Hello, welcome to the video lecture series on digital image processing. Now, in today's class, we will talk about another spatial domain technique which is called mask processing technique. The previous lectures also were dealing with the spatial domain techniques, and we have said that image enhancement techniques can broadly be categorized into spatial domain techniques and frequency domain techniques. The frequency domain techniques we will talk about later on. So, in today's class, we will talk about another spatial domain techniques which are known as mask processing techniques, and under this we will discuss three different types of operations. The first one is the linear smoothing operation. The second one is a nonlinear operation which is based on the statistical features of the image, which is known as the median filtering operation. And the third kind of mask processing technique that we will talk about is the sharpening filter. Now, let us see what this mask processing technique means. Now, in our earlier discussions, we have mentioned that while going for this contrast enhancement, what we basically do is, given an input image say f x y, we transform this input image by a transformation operator say t, which gives us an output image g x y. And what will be the nature of this output image g x y? That depends upon what is this transformation operator t. In point processing technique, we have said that this transformation operation t that operates on a single pixel in the image, that is, it operates on a single pixel intensity value. But as we earlier said that t is an operator which operates on a neighborhood of the pixels at location x y. So, for point processing operation, the neighborhood size was 1 by 1. So, if we consider a neighborhood of size more than 1, that is, we can consider a neighborhood of size say 3 by 3, we may consider a neighborhood of size say 5 by 5, we may consider a neighborhood of size 7 by 7 and so on. So, if we consider a neighborhood of size more than 1, then the kind of operation that we are going to have, that is known as mask processing operation. So, let us see what does this mask processing operation actually mean. Here we have shown a 3 by 3 neighborhood around a pixel location x y. So, this outer rectangle represents a particular image, and in the middle of this we have shown a 3 by 3 neighborhood, and this 3 by 3 neighborhood is taken around a pixel at location x y. By mask processing, what we mean is, so if I consider a neighborhood of size 3 by 3, I also consider a mask of size 3 by 3. So, you find that here on the right hand side we have shown a mask. So, this is a given mask of size 3 by 3, and these different elements in the mask, that is w minus 1 minus 1, w minus 1 0, w minus 1 1, w 0 minus 1 and so on up to w 1 1, these elements represent the coefficients of this mask. So, for all these mask processing techniques, what we do is we place this mask on this image where the mask center coincides with the pixel location x y. Once you place this mask on this particular image, then you multiply every coefficient of this mask by the corresponding pixel on the image, and then you take the sum of all these products. So, the sum of all these products is given by this particular expression, and whatever sum you get, that is placed at location x y in the image g x y. So, by mask processing operation, this is the mathematical expression we get, that g x y equal to w I j into f x plus I y plus j you have to take the summation of this product over j varying from -1 to 1 and I varying from -1 to 1. So, this is the operation that has to be done for a 3 by 3 neighborhood, in which case we get a mask again of size 3 by 3. Of course, as we said that we can have masks of higher dimension, we can have a mask of 5 by 5 if I consider a 5 by 5 neighborhood. I have to consider a mask of size 7 by 7 if I consider a 7 by 7 neighborhood, and so on. So, if this particular operation is done at every pixel location x y in the image, then the output image g x y for various values of x and y that we get is the processed image g. So, this is what we mean by mask processing operation. Now, the first of the mask processing operation that we will consider is the image averaging or image smoothing operation. So, image smoothing is a special filtering operation where the value at a particular location x y in the processed image is the average of all the pixel values in the neighborhood of x and y. So, because it is average, this is also known as averaging filter, and later on we will see that this averaging filter is nothing but a low pass filter. So, when we have such a averaging filter, the corresponding mask can be represented in this form. So, again here we are showing a mask, a 3 by 3 mask, and here you find that all the coefficients in this 3 by 3 mask are equal to 1. And by going back to our mathematical expression, I get an expression of this form, that is g x y equal to 1 upon 9 into f x plus I y plus j, take the summation over j equal to -1 to 1 and I equal to -1 to 1. So, naturally, as this expression says, you find that what we are doing, we are taking the summation of all the pixels in the 3 by 3 neighborhood of the pixel location x y and then dividing this summation by 9. So, which is nothing but average of all the pixel values in the neighborhood of x y, in the 3 by 3 neighborhood of x y, including the pixel at location x y, and this average is placed at location x y in the processed image g. So, this is what is known as averaging filter, and also this is called a smoothing filter. And the filter and the particular mask for which all the filter coefficients or mask coefficients are same or equal to 1 in this particular case, this is known as a box filter. So, this particular filtering operation that we are getting, this particular mask is known as a box filter. Now, when we perform this kind of operation, then naturally, because we are going for averaging of all the pixels in the neighborhood, so the output image is likely to be a smoothed image. That means, it will have a blurring effect, all the sharp transitions in the images will be removed and they will be replaced by a blurred image. As a result, if there is any sharp edge in the image, the sharp edges will also be blurred. So, to avoid the effect of blurring, there is another kind of mask, averaging mask or smoothing mask, which performs weighted average. So, such a kind of mask is given by this particular mask. So, here you find that in this mask, the center coefficient is equal to 4, the coefficients vertically up, vertically down or horizontally left, horizontally right, they are equal to 2, and all the diagonal elements of the center element in this mask are equal to 1. So, effectively what we are doing is, when we are taking the average, we are weighting every pixel in the neighborhood by the corresponding coefficients, and what we get is an weighted average. So, the center pixel, that is the pixel at location x y, gets the maximum weightage, and as you move away from the pixel locations, from the central location, the weightage of the pixels are reduced. So, when we apply this kind of mask, then our general expression of this mask operation that is valid, which becomes W I j f x minus I y minus f x plus I y plus j, take the summation from j equal to minus 1 to 1 and I equal to minus 1 to 1, and take 1 upon 16 of this, and that will give the value which is to be placed at location x y in the processed image G. So, this becomes the expression of G x y. Now, the purpose of going for this kind of weighted averaging is that because here we are weighting the different pixels in the image for taking the average, the blurring effect will be reduced in this particular case. So, in case of box filter, the image will be very blurred, and of course, the blurring will be more if I go for bigger and bigger neighborhood size or bigger and bigger mask size. When you go for averaging, weighted averaging, in such cases the blurring effect will be reduced. Now, let us see what kind of result we get. So, this gives the general expression that when we consider W I j, we have to have a normalization factor, that is, this summation has to be divided by sum of the coefficients, and as we said that 3 by 3 neighborhood is only a special case. I can have neighborhoods of other sizes. So, here it shows that we can have a neighborhood of size m by n, where m equal to 2 a plus 1 and n equal to 2 b plus 1, where a and b are some positive integers. And obviously, here you show that here it is shown that the mask is usually of odd dimension, it is not even dimension, and that is normally the mask of odd dimension which is normally used in case of image processing. Now, using this kind of mask operation, here we have shown some results. You find that the top left image is a noisy image. When you do the masking operation or averaging operation on this noisy image, the right top image shows the averaging with a mask of size 3 by 3. The left bottom image is obtained using a mask of size 5 by 5, and the right bottom image is obtained using a mask of size 7 by 7. So, from these images it is quite obvious that as I increase the size of the mask, the blurring effect becomes more and more. So, you find that the right bottom image, which is obtained by a mask of size 7 by 7, is much more blurred compared to the other two images, and this effect is more prominent if you look at the edge regions of these images. If I compare this particular region with the similar region in the upper image or the similar regions in the original image, you find that here in the original image is very sharp, whereas when I do the smoothing using a 7 by 7 mask, it becomes very blurred, whereas the blurring effect when I use a 3 by 3 mask is much less. Similar such result is obtained with other images also. So, here is another image, again we do the masking operation or the smoothing operation with different mask sizes. On the top left, we have an original noisy image, and the other images are the smoothed images using various mask sizes. So, on the right top, this is obtained using a mask of size 3 by 3. The left bottom is an image obtained using a mask of size 5 by 5, and the right bottom is an image obtained using a mask of size 7 by 7. So, you find that as we increase the mask size, the reduction is in noise, or the noise is reduced to a greater extent, but at the cost of addition of blurring effect. So, though the noise is reduced, but the image becomes very blurred. So, that is the effect of using the box filters or the smoothing filters, that though the noise will be removed, but the images will be blurred, or the sharp contrast in the image will be reduced. So, there is a second kind of image, second kind of masking operations which are based on order statistics, which will reduce this kind of blurring effects. So, let us consider one such filter based on order statistics. So, this kind of filters, unlike in case of the earlier filters, these filters are non-linear filters. So, here in case of these order statistic filters, the response is based on the ordering of the intensities, ordering of the pixel values in the neighborhood of the point under consideration. So, what we do is we take the set of intensity values which is in the neighborhood, which are in the neighborhood of the point x y, then order all those intensity values in a particular order, and based on this ordering you select a value which will be put at location x y in the processed image G, and that is how the output image that you get is a processed image, but here the processing is done using the order statistics filter. Thank you.